Alright, the derivative today, which is a pretty big concept, so this video, you might be able to see, is a little bit chunkier, but stay with me, it's a really important concept and one that you really want to understand very well. So last time we began with a car on a parabola or some other curve, and we imagined running this like a little roller coaster along the curve, and we were interested in tracking the slope of the curve at each point in time, right? And so we even started drawing graphs of this. We realized that the slope is always changing as you run along the curve, and so we thought about graphing this, right? And we came up with red lines that looked a bit like this, where the red line is the gradient function of the yellow line, right? But there were two problems, I think. One was, how did we even know that it was going to be a line, right? So how do we precisely know the nature of this gradient function? But number two, perhaps the most important problem we saw last time, was what do we even mean when we talk about the gradient at a point? Because the whole concept of gradient doesn't allow you to think of a single point. So how do you make sense of that? Okay, but we'll start with that first question. Given the equation of a curve, how do you find its gradient function, or how do you describe its gradient at any value of x? All right, once again, we'll start with straight lines. I think it's always important to start from this thing that we know very well. I'll tell you the gradient is 2, and we want to think about what that means. So it means that if I move the x across by 1, the y moves up by 2. So write that down. Moving x by 1 results in moving y by 2. Right, likewise, if I move the x across by 2, then the y moves up by 4. You can write that down. Moving x by 2 results in moving y by 4. Same thing for 3 and for 6. And I'm being quite repetitive with this. The idea is that gradient is trying to analyze what effect moving x has on y. Whenever you move the x value, that always produces some change in the y value. And the gradient is about trying to measure that change. Right, that when you change x by a little bit, which I'm going to call dx, right, what change does that produce in the y value, dy? Okay, so I'm saying moving x by some dx results in moving y by dy. And in our case, the gradient being 2 means that dy is double dx. Or we can even say dy over dx equals 2. That's just rise over run, right? Now, I'm being a little bit intentional with the language I'm using. Dx and dy are they're quite loaded terms. Just a word of warning, dx does not mean d times x. Dx is a single object. It means I'm moving the x by a little bit. Okay, I'm going to really try and use the colors to keep that clear throughout the rest of this. Okay. Alright, so back to the parabola then. I've got even some numbers on it this time. Let's start by looking at a single point. That point I've drawn there in red at 1, 1. Okay, I'm going to try a similar analysis with this. When I'm trying to work out the gradient, well, I have to have some kind of movement. I have to move x across by a bit and see what effects that has on the y. So let's just move forward by some amount. I'm going to say 2. That little blue 2 there means I want to move this red point across by 2 and see what change in the y value that produces. So let's move it. Let's go. Off it goes. All right. And again, the amount we've moved across is just 2. But what change has that produced in the y value? Well, before it was 1, and after it's 9. So the change it's produced is 8. Okay, well, moving across by 2 produced a change in the y value by 8. So does that mean the gradient is 8 divided by 2, which is 4 then? Does that make sense? Well, hopefully you can see it doesn't really. And the reason for that is if you look at those 2 red points, I've left a kind of shadow at 1, 1 where it began, and I put my roller coasters there. What you can see is that, well, they have very different gradients. Just by looking at those 2 roller coasters, you can see that the gradient has changed a lot between x equals 1 and x equals 3. So it's like by the time we've measured the gradient, it's already changed, because the curve is made of a changing gradient, really. That's what makes it curving, right? And so by the time we've measured gradient, well, it's changed already. So that's a problem. Well, what if we tried something a bit different then? What if we only moved forward by 1 this time? So we're going to grab that red point at 3, 9 and slide him a little bit closer to 1. What happens then? All right. Well, let's measure those distances again. So we said we moved forward by 1. What change did that produce in the y value this time? How long's the pink line? Well, shoot it across. It's the difference between 1 and 4, which is 3. And so moving across by 1 this time produced a change in the y value of 3. So is the gradient now 3 divided by 1? Is the gradient now 3? Well, I think the same problem's there, right? Because if we put those roller coasters back on, we can see that it's better, but the gradient has still changed on us, right? And that's, again, the problem that we have, the sort of paradox of trying to work out the gradient at a point, is that the gradient requires you to move your point. But then once you've moved your point, you've changed the gradient. So how do you get a handle on this? How do you grasp that thing that's always moving away from you? Well, here's what they did at the very beginning of calculus. They saw that if you got that roller coaster and you moved it closer and closer and closer to 1, you get more and more and more accurate. All right, so we're going to do this whole thing again, but this time, rather than say move forward by a fixed number like 1 or 2, we'll do it all again, but using generic algebra, with the intention of eventually moving those 2 points closer and closer together. Okay, so we'll start again. Put the point there. It's now at some generic value of x, which we don't know or care about. We slided it across. Now I've made that slide really big, but again, our intention eventually is to make that distance between those 2 points get really, really, really small. Okay. Now, the blue line has length dx. The pink change in the y value that moving across by dx produces is what we called dy. Right, and now I said before, when I use those sort of language of dx and dy, I'm sort of being quite intentional with that. Really, whenever we use dx or dy to represent a change, I'm sort of hinting to you, or you're hinting to whoever's reading what you're writing, that you have every intention of making these 2 values shrink towards nothing. Okay, so we're trying to eventually shrink them, but for now, we'll keep them here for clarity's sake. So there they are. Right, the red point has moved somewhere. So what's its new x value? Its new x value must be x plus dx, because we've moved forward by dx. Okay. Now, what about the y values? Well, to start with, because this is the graph y equals x squared, the y value at x is just x squared. And where has it moved? Well, it's got a new y value, and that must be x plus dx squared, right? Because the new x value was x plus dx, and so we have to square that to get the y value. So we put that in brackets and we square it. The gradient is dy over dx, and so we calculate that. Now, what's dy? dy is the change in the y value, which we calculate by subtracting the old y value from the new y value. So that's why the top is x plus dx all squared minus x squared. Okay, it's just measuring that change in y values. We expand that out. Again, I'm using color to remind you that dx is not d times x, it's its own little object. So we expand out that bracket with the x plus dx, we get this, right? The x squared and x squared will cancel because it's x squared minus x squared. So that means that up top, we're only left with 2x dx plus dx squared. And at this point, we can divide out the dx, right? Because there's a dx in the 2x dx and in the dx squared. And so we can divide that out entirely, leaving us with just 2x plus dx. and that's what dy dx equals. Okay. Now let's bring back the work we did before when we moved forward by 2 and forward by 1 and see if that matches what we've just discovered, right? Because I'm saying that when we do this sort of process, dy over dx is always 2x plus dx. So let's see if that works, right? So for example, look at that top one. When we moved forward by 2, this was at x equals 1, so 1 can go in there. We moved forward by 2, so it's like we chose dx to equal 2, and 2 times 1 is 2, 2 plus 2 is 4, so that did work. All right. What about when we move forward by 1? Well, once again, the x value we started with was 1. We moved forward by 1, so we chose dx to equal 1, and 2 times 1 is 2, plus 1 is 3. And so we worked out that's why the gradient was changing on us, right? Because the gradients actually just double the x value, then you had to plus that blue number dx. And so as we changed that blue number, our calculated gradient was also changing the whole time. Okay, so that makes sense. That works out then. But what we said before, we did this with every intention of making dx approach 0. We saw that the most accurate measurement of gradient would happen as dx and dy both shrink towards 0. And if this shrinks towards 0, that means the dx is going to vanish there. And so dy dx is just equal to 2x. Right. Now, notice what I'm not saying. I'm not saying dx equals 0. It might look like that from the second last line to the last line. It might look like we just cancelled the dx and the dx equaled 0. I'm not saying that. Right? Dx is not equal to 0. Neither is dx a number infinitely close to 0. There's a branch of maths that deals with that. It's called non-standard analysis because it's not standard. So we're not saying that. We're saying dx is a properly real positive number. But what we're thinking about is what happens when that positive number gets closer and closer and closer and closer to 0. That's what we're thinking about. Okay, and what we find is that dy dx, that gradient value, gets closer and closer and closer and closer to 2x. And so we say that gradient then we'll say is equal to 2x. Okay? Now, we're not left without a geometric interpretation of this, because if you took 2 points and you joined them with a line, right, and you brought those 2 points closer and closer and closer together, what you find is that the line actually becomes what we call a tangent to the curve. So there is a nice geometric interpretation of this squishing 2 points closer and closer together thing that we just did. Right, and actually, because it coincides with the tangent, then the gradient of this red tangent line, right, is exactly what dy dx is measuring. And so what we just worked out is that dy dx is 2x, and the meaning is that the gradient of this red tangent line is always double the x value. So this red line right now is a very steep downhill, right, because x is negative. So double x is a pretty big negative number, right? And as this runs along the curve, you're going to find that the gradient of the red line is always double the x value. Okay? All right, that's a lot we've just covered there. So let's try and tie those threads together. The example we saw was for y equals x squared, the parabola, the gradient is dy dx, which is 2x. That is the gradient function. That's why last time we ended up with a straight line, right? Because it's just 2x. Okay, so keep a picture in mind. What does that mean? It means given any x value, the gradient of that, say, roller coaster sitting at that point is just double the x value. So this is a function that tells you the gradient wherever you are. Okay? Now, this next part might seem strange, but I'm going to say dy dx isn't actually a fraction. Okay, the sort of road to where we are now, we started with it being a fraction, right? But it's not really a fraction anymore. Rather, for any value of x, it expresses the number that gradient, that the fraction we were working with will approach as that blue dx length approaches 0. Right, that's what we were talking about before, with that dx is not equal to 0, neither is it a number infinitely close to 0, but dy dx is a way we express where does that gradient approach? What number does that gradient get closer and closer and closer to as dx gets closer and closer and closer to 0? Now notice I use that word around the x value. That's really important. We'll get to that soon. But the word around means that I care about what's happening on both sides of the x value. All right. We haven't made that clear in our animation so far, but it's important. Okay. We saw that this is the same as working out the gradient of the tangent at that point, which is that red line I'm drawing now that just touches the parabola at one point. Okay. And the language we use is we say it is a function that gives you the gradient at each point on the curve, because that's the most, I guess, the most sensible way to talk about it. But again, behind that language of gradient at the point, what we really mean is the gradient of 2 points very, very close together around that point. Okay, and so that's the number we assign to the gradient at that point. Okay. So we'd say at x equals 1, the gradient is 2 times 1, which is 2. At x equals, say, 3, so at the point 3, 9 for a parabola, the gradient would be 2 times 3, which is 6. And at x equals 0, the gradient is 2 times 0, which is 0. And that's what we meant by by saying that the parabola is flat at that vertex. At that point where x equals 0, the parabola is flat. It's got a gradient of 0. Okay? You might want to write this stuff down as we go, and you might want to rewatch this a couple of times just to make sure you've understood all the subtleties here. But let's go on. Terminology. So how we write this stuff. Let's go to a generic function now, not just y equals x squared, but any function. The gradient of the function is calculated by working out this guy. Now you might be like, what is that guy? We haven't seen that guy before. No, we kind of have, right? So stay with me here. The yellow boxed thing, that's just f of x, which means what's the y value at a certain x value. The x plus dx bit is f of x plus dx, which means what's the y value at x plus dx, which means what's the y value after moving x forward by some length dx. Okay? And so when you subtract those, you're really subtracting some old y value from some new y value after moving x forward by dx. And so the whole top here in this fraction is just expressing some difference in y values. We call that dy. Okay, so I hope you're satisfied that this is just using some function notation to really express that idea of change in y over change in x, dy over dx. Okay, but that wasn't all, because after calculating this as an algebraic thing, again, we did this with every intention of making this dx number slide towards and approach 0. The way we write this in maths is we call this a limit as dx goes to 0. Okay, it's fancy language, but all it means is let dx, let this blue length, however far we moved x forward by, let this number get closer and closer and closer to 0 and see what happens. Okay, now the important thing with a limit is dx never touches 0. Again, dx never equals 0. It only gets closer and closer and closer. Okay, and so that's what we do. All right. The result of this, so for x squared, the result of doing this was we got 2x. That 2x is called the derivative of x squared. In general, the derivative is just the gradient function with respect to x being our variable that's changing. Right? We call it dy dx as we've seen, but we also call it y dash or f dash x, okay? Because sometimes writing dy dx just gets a little bit painful, and so we can just use a dash to represent the derivative, the gradient. Okay, so really in your head, I hope derivative is really the same word as gradient. It really should be in your head. Okay, verb form we say is to differentiate, f of x. So if the question is differentiate x squared with respect to x, the answer would be 2x. Okay, it's just a verb of what we just did. Okay. Now, sometimes this process of working out this gradient and then sliding dx to 0 doesn't really give you a sensible answer. All right, we say this limit does not always exist, in which case the function is not differentiable. All right, not everything can be differentiated. It doesn't always make sense to find the gradient of a curve, and the intuition is the curve has to be sufficiently smooth. If it's not sufficiently smooth, then it won't make sense. Let me show you. So a non-differentiable function. And the most typical example would be the absolute value. Okay, let's just see what happens if you run the roller coaster. Okay, so we start the roller coaster here, and we run him along this this little curve, or not really a curve, it's a graph, and off he goes. All right, I might have taken a bit of creative liberty with what happens to him, but something happens at that point, doesn't it? Something weird happens there. Imagine you were on the roller coaster and you were on that curve. It would not be a very pleasant experience, right? Why is that? Look at that red point. dy dx at this point asks for what? The gradient around this point, right? Where if you move x by some dx, and again, I didn't animate this before, but really it's when you move x by dx in any direction, what's the gradient look like around that point? If you just move a tiny little bit. So we do that. We move it a tiny little bit. Now look at the left with me. Look at that point that's moved to the left. Here, it looks like the gradient is -1. It's going downhill with a slope of 1, so it's a -1 gradient. But if you look on the right, that part looks like the gradient is +1. Right? If you move a little bit to the right, it's going uphill, and it's got a gradient of 1 this time. Right? And so because these two sides do not agree, what that tells you is the limit does not exist. It doesn't make sense to assign any single number to the slope at that point. Okay? And so in general, you cannot differentiate sharp corners, okay? Because they have this disagreement in gradient on either side of that point. I'll show you another example. Maybe this one's more obvious. If a function like this is not continuous, if it's broken like this and it jumps or in some way is not a continuous function, you can't measure gradient when you teleport. That's just bad news, all right? And so a function must be continuous for it to have any chance of being differentiable. We might have a closer look at exactly what continuous means later, but intuitively just means a function cannot jump or cannot do something of that nature. All right. My language is it must be continuous for it to have any chance of being differentiable, right? But it doesn't mean that any continuous function is automatically differentiable, unlike what your book says, right? So what we saw just then with the sharp corner on y equals absolute value of x shows that you can be continuous, but not differentiable. All right, let's end with a differentiable function that often gets mistaken for being not differentiable. I'm pretty sure your textbook says that this function is not continuous and therefore it can't be differentiable. That is not true at all. So let's look at why, right? Your book will say that this is not continuous because there's a gap at 0. You can't draw this graph without taking your pen off the paper, right? But there's a problem, right? This, where I've put my red arrow, that can't be an issue. That can't be a problem because there is literally nothing to see here. Right? What happens at x equals 0 has nothing to do with our function, has nothing to do with our graph at all, and so you can't label that as a problem. So actually, this function, y equals 1 over x, is continuous, is differentiable. Okay? And let's differentiate it as practice. Right. So what did we need to do? We needed to look at that f of x plus dx minus fx over dx thing, right? But I'm going to sub in what that means straight away, because all we're doing is we are looking at the change in y values, so the change in 1 over x if I move x forward by dx. Okay, so that's why my new y value is 1 over x plus dx. My old value is just 1 over x. I subtract them on top and divide by how far I moved, dx. All right, this fraction is a bit weird. It's got fractions inside fractions. That's not cool. So what we're going to do is multiply by both of those denominators upstairs. So that's both x and x plus dx. But of course, we need brackets for that. And we're going to multiply everything we see by x, bracket, x plus dx. Okay, it's just details of algebra here. So let's see what happens. On the first term, the 1 over x plus dx, well, that denominator is going to cancel the x plus dx, leaving you with just x. On the right, the x on the bottom will cancel with the x we multiplied, leaving you with just x plus dx. And on the bottom, it has to get multiplied. So that's what you get. All right. On top now, x minus x cancel, but remember the minus also applies to dx. On the bottom, we can expand. We get this. Okay. And now we can see the dx on top cancels with the dx on the bottom, and so you now only have negative 1 over x squared plus x dx. So that's just working out the algebra, okay? Work through that yourself slower if you need to, but that's just the algebra. But again, we did all of this with the intention of making dx get closer and closer and closer to 0 and seeing what happens to this gradient when we do that. So dy dx is where you limit that blue dx to 0. And when you limit that to 0, well, that dx guy will just vanish. And so you're left with negative 1 over x squared. And so the derivative of 1 over x, the gradient of the hyperbola 1 over x, is actually negative 1 over x squared. Right. You'll notice because x squared is always positive, negative 1 over x squared is always negative. And the meaning of that on the hyperbola is as you travel from left to right, you are always going downhill. Okay, because the gradient is always negative. So that's how we're going to differentiate for the time being. There is a quicker way for most things, but this is the first way you should see because I think it's the most informative in terms of what it tells you about what's actually happening when you differentiate. Okay, so never lose sight of this. Remember, when you differentiate, you're just working out the gradient of the function at each point, which again was a paradox, but I think what we did here, what the founders of calculus discovered, which is what we just talked about, is a really clever way of sort of sidestepping that paradox. So it's really cool. All right, well, that's it. Hope that made sense. Thanks for watching, and I'll see you guys next time.